Today we are going to talk about an example, a numerical example, to see how to obtain the shear stress distribution in a thin walled cross-section beam due to the applied shear stress. Okay, so the picture that is drawn here shows the cross section of a beam. It's a thin walled jet-like cross section. Okay, the uniform thickness, it has a uniform thickness of T. So it has uniform thickness So our job is to find out what is going to be the shear stress distribution in this cross section due to applied shear force Sy. So shear force applied shear forces are Sy and Sx is equal to 0. Sx is equal to 0. So I have only one shear force that is shown by this red color arrow, which is applied in the y direction. So this is the x-axis, this is the y-axis. Okay, so we have seen earlier that the equation for the shear force that we have derived in the last class is something like this. We have seen that it is Qs minus Q0 Okay, so this is the expression that we have derived in the last class, where Qs is the shear flow in the cross section, okay, along the cross sectional local coordinate S. Now for this particular problem, we know that Sx is equal to 0. Okay, so this expression therefore simplifies, and I say Qs minus Q0 is going to be Sy Ixy Okay, so for this particular problem, I get this expression for Qs minus Q0. Okay, now so the first thing that we need to do, so we have to assume that Sy is known to us. So the first thing that we have to do is to find out the sectional property Ixx, Iyy and Ixy. So let us try to find that. Okay, let me erase this off. Okay, so if I try to find out the sectional property, So I will not find it again, I will just give you the answer, because by now I guess all of you all are confident in finding out the sectional property of a thin wall cross section. So Ixx for this particular cross section is h cube t by 3. Iyy for this particular cross section is h cube t by 12, and Ixy is h cube t by 8. Okay, so if I plug in these values into this equation, so let me call it as equation 1. So by substituting these values, okay, and doing the calculation, we can see that it is going to look somewhat like this. So Q0 Qs minus Q0 is going to be Sy by h cube integral 0 to s 10.32x minus 6.84y into ds. So let me call this as my equation 2, okay, for this particular case. Now let us see, now we have, till this point it is pretty straightforward, right? You have to just plug in number into an equation that we have already derived, and that's all we have done. So it's till this point there is nothing to worry about. Now let us see how to implement this equation for this given cross section and find out the shear stress distribution. So I would need this figure, so let me clean this up. And just keep this in handy, Qs minus Q0. Okay, so this is my equation 2. Now we have to implement it. So let me just put numbers to this different points of the cross section. So this point I am calling it as 1, this point to be 2, this point to be 3, and this point to be 4. So I have marked all the discontinuity point on the cross section as 1, 2 and 3, 4. Okay, now for flange 1, 2, how are we going to implement? So for flange 1, 2, okay, how are we going to implement it? So S is in this direction. So S is in this direction, right? So we are taking this to be the direction for S. Right? So if S is in this direction, for flange 1, 2, S is going to lie between h by 2 and 0. So for portion 1, 2, my S is going to vary between 0 and h by 2. Right? Now, so what I have to do is that I have to evaluate equation 2 for flange 1, 2, where S is going to vary between 0 to h by 2. But in order to evaluate the integral of equation 2, I need to express x and y in terms of s, because the integral is in s. So let me find out what is x in terms of s. If we look into it, x in terms of s is, so if I take this point to be s equal to 0, then x in terms of s is minus h by 2 plus, So when s is equal to 0, x, so this is going to be x. So see, when s is equal to 0, x is minus h by 2, and when s is equal to h by 2, x is equal to 0. So this is the correct form of x. Okay, so now let me see what is y in terms of s. So y is always minus h by 2, right? So now we are all set to solve this equation. So let me write as qs minus q0 is therefore going to be q12. My s is varying between 1 2, so q12 minus q0, and that is going to be equal to sy by h cube 0 to s 10.32 into minus h by 2 plus s minus 6.84 into minus h by 2, and that with the integral s. So that is going to be, if I evaluate the integral, this is going to be sy by h cube into if I evaluate this integral, this is going to be 5.16 s square minus, you do it for yourself and see whether this is correct, minus 1.74 hs. If I evaluate this integral and substitute the, so I will better not skip this intermediate step. Let me write it down. So if I evaluate this integral, this is going to be sy by h cube into 10.3 plus 6.84. So that is going to be how much? That is going to be 0 to s 6.84 minus 10.3 is 4. It is going to be 1.74. Yes, so that is by 2 is going to be 1.74. Okay, so am I doing it correctly? I hope so. Okay, so it is going to be minus 1.74 h, okay, plus 10.32 s into ds. So if I evaluate this integral, this is going to be sy by h cube, and then I have minus 1.74 hs plus 5.16 s square, the limit between 0 to s. So often why I did this intermediate step is that often the students make a mistake and replace this limit, instead of writing it as from 0 to s, they write the limit as from 0 to h by 2, which is not correct. See, I am finding the shear stress distribution, right? Q12 is the shear stress distribution in the flange 1-2 or in the portion 1-2. So Q12 is a function of S. Okay, because Q12 is going to vary with S, so it is not a single valued number, so it's a function of S. So I shouldn't replace the integral with some definite value. It has to be from 0 to s. That one should keep in mind. So if I evaluate, therefore this integral turns out to be sy by h cube into 5.16 s square minus 1.74 hs after substituting the limits. Okay, now that is my q12, which is a function of s minus q0, right? This is what I have found out. Let me call it as equation 3. Now my point is, what is q0? Okay, the value of q0, so everything is not now known to me except q0. So what is the value of q0? So q0 is the value of the shear stress at point 1, which is a free edge, okay, which is the open edge of the cross section. Therefore, at a free surface or at a free edge, all the stresses should be equal to 0 unless there is an externally applied surface force there. So q0 has to be equal to 0. Okay, so that makes my life much more simpler, and I can write this as q1 to s is going to be equal to this expression. Okay, so therefore I see that the shear stress, so what is the meaning of this? The meaning of this is that shear flow rather, or shear stress if you want to say it, q1 to s in portion 1 2, we call it flange if it is horizontal, flange 1 2 is a function of, is varying according to, let me not call it a function, is varying according to the equation three. So q1 2, or the shear flow in portion 1 2, is varying according to the equation 3. Okay, so it is going to be a parabolic variation. I can even draw the variation. Let us try to draw the variation. So if I draw the variation with this green color, so it is, or maybe with red color, so it is going to look something like this. So this is my q1 to s. Okay, if you see till some position where qs is 0, that is for so here q1 to s is 0, here it is negative, the value is negative, so the direction of shear flow is opposite to the positive direction of s, and here it is positive. Okay, so it is in the positive direction of s. Now let us find out what is q2, okay, or shear flow at point 2. What is that? So here I have to put s equals to h by 2. So by substituting s equals to h by 2 in equation 3, I will get that q2 at s, q2 is going to be 0.42 sy by hq. By, if I put the value of q2 here, so it is going to be 0.42 sy by h. Okay, so this is the value of q2. So therefore this portion is q2, which is 0.42 sy by h. Okay, right? So so fine, so so we have been able to find out the shear flow distribution in the portion 1 2. So the now the next job is to find out the shear flow in portion 2 3. So let me erase this off. this I would need. Okay, now let me see for web. So I'm not now going to be considering this portion. So this portion between 2 and 3, so S is in this direction. So for this portion, S is going to lie between H to 0. Okay, 0 at 2 and H at 3. Now again I have to need to express X and Y for portion 2 3 in terms of S. So what is X going to be? X is always 0 irrespective of S for portion 2 3. And then Y, what is Y? Y is equal to minus H by 2 plus S. Okay, so now what I have to do is that I have to say that QS minus Q0 for this portion is Q23, which is a function of S, minus Q0. Now 0 here is 2. So Q basically Q at point 2, and that is going to be equal to Sy by H cube 0 to S 10 point, this is going to be 10.2332 into 0, X is 0, minus 6.84, Y is minus H by 2 plus S into ds. Okay, so that is going to be, if I simplify this, Q23 S minus Q2 is going to be Sy by H cube 0 to S, and that is going to be 3.42 H minus 6.84 S into ds. So if I integrate this, I am going to get this as Sy by H cube into 3.42 HS minus 3.42 S square 0 to S. That eventually is going to be Sy by H cube into 3.42 HS minus 3.42 S square. Okay, so that is going to be the solution for the expression. So I'm just checking whether I have done it correctly. Okay, so this seems to be correct. Okay, so but of course I always suggest that you do it for yourself and figure out whether this is correct or not. So 10, therefore this is going to be Q23S minus Q2. Now Q2 I have seen is 0.42 Sy by H. Therefore Q23 S is going to be 0.42 Sy by H plus Sy by H cube into 3.42 HS minus 3.42 s square. Okay, that is my fourth equation. So this is my fourth equation. Okay, and if I try to find out the solution of this, or how this varies, then this is going to look something like this. Okay, where this is also 0.42 sy by h, and this portion is also 0.42 sy by h, and this is going to, okay, so we see that this is the variation of Q2 of shear flow in the portion 2, 3. Now from this expression, I can see that what is Q3? Q3 is going to happen at S equals to H. So Q3 is also, if you put the value of S is equal to H, you will see that is going to be 0.42 sy by H. So at point 3, this is also going to be 0.42 sy by H. Now this is a good check, okay, because the cross section is antisymmetric. Okay, there is an antisymmetry in the cross section. The value of the shear flow at 2 should be equal to the value of shear flow at 3. Okay, that should happen there. Now for the portion, so this is a good check. So what you can do is that you can take the expression of Q23, find the value of shear flow at Q3, and that should be equal to Q2 because there is an antisymmetry. You can also do similar checks for a symmetric cross section, okay, which is always going to show you whether the calculation that you have done is correct or not. Okay, so now the next job is to find out for portion for flange 3, 4. So for flange 3, 4, again I can say S is going to be between h by 2 to 0. X is going to be h by 2 minus S, and y is going to be h by 2. Okay, x, let me see, when s is equal to 0, when s is equal to 0, I have done a mistake here. So x by 2 has to be just s. When s is equal to 0, x is equal to 0. When s is h by 2, x is also h by 2. And y is always going to be h by 2. So let me write it, x is equal to s. So you can say Q34s minus Q0, where Q0 is Q3, is going to be sy by h cube 0 to s 10.32x minus 6.84 y into ds, where x is s and y is h by 2. And you can find out, you can very easily find out Q34s could be very easily find out, because I know Q3 is 0.42 SY by H. Okay, that you can easily find it out. But we can also say, because of antisymmetry, the distribution of the shear flow in this cross section is going to be just antisymmetric of this, and this is going to look exactly similar to the bottom flange, only the direction is going to be different. So this is going to be positive, and here it is going to be negative. Positive as in the direction of S, and negative as in the opposite direction of S. Okay, so with this, I think the concept of shear flow or shear stress distribution in a thin wall cross section due to applied shear stresses is well understood. Though I have done it only for a case where only Sy is acting and Sx is 0, you can pretty well implement the method where both S and Y, Sy and Sx are non-zero, or where Sy is 0 and Sx is non-zero. Okay, so thank you.